Alright, so in this video I'm gonna be explaining this important article with the title Distance Encoding, Design Provably More Powerful Neural Networks for Graph Representation Learning. This paper in NeurIPS 2020. Learning representations of sets of nodes in a graph is crucial for applications ranging from node role discovery to link prediction and molecule classification. For example, classification of enzyme, peptides, proteins that are available in PyTorch geometric and you can use them. So graph neural networks have achieved great success in graph representation learning. However, expressive power of GNNs is just limited to this one WL test, and thus GNNs generate identical representations for graph substructures that may in fact be very different. More powerful GNNs proposed recently by mimicking higher order WL tests only focus on representing entire graphs, and they are computationally inefficient as they cannot utilize sparsity of the underlying graph. Here we propose and mathematically analyze a general class of structure-related features termed distance encoding. Distance encoding assists GNNs in representing any sets of nodes while providing strictly more expressive power than one WL test. And it captures the distance between the node set whose representation is to be learned and each node in the graph. To capture the distance, encoding can apply various graph distance measures such as shortest path distance or generalized PageRank scores. So we propose two ways of GNNs to use this distance encoding. One as external features, the second one is as a controllers of message aggregation, which I like this one more than the first one. The first one is trivial, but the second one is very interesting. Both approaches can utilize the sparse structure of the underlying graph, which leads to computationally efficiency and scalability. So, we have this graph G, and the node permutation, we call it pi, is just a bijective mapping. A function is invariant if f of s with f of permutation of s is the same. So we say the structural representation of a tuple S and A is a invariant function, and the invariant property is critical for the inductive and generalization capability, as its free structural representations from node identifiers and effectively reduces the problem. By the way, I have a playlist for geometric deep learning, which I talk about equivariant and invariant representations, which is related to this area as well. So if structural representations are different over any two non-isomorphic tuples, then for any invariant function it can be universally approximated by feeding it into three-layer feed-forward neural network, as long as the feature space is compact and f is continuous. So this is a slide from Professor Panley. You see we have this readout when for each of them we see the computational graph of that in two hops, and then we can represent any set that you say. For example, this set S here, which consists of only A and F. So we can represent what is the representation of S, set S. And A is just this, for each edge we have from vertices to vertices, and also your vector representation, which has d attributes, d features. So you see a 3 regular graph with 8 nodes. So briefly assume that all node attributes are the same, and the nodes can only be distinguished based on their network structure. So it's very easy. We just use F1 and F2, and so we aggregate and then combine. So we update like this. But in this paper is mostly focused on this WL test for this representation, that our solution, as I said, is based on distance encoding. So I just borrow another slide from Professor Panley, that theta of U condition on V. So here U is a node and S is still a set, but U and V both of them are nodes. So you see, this is very similar. I mean, it is in the spirit of that personalized PageRank and everything we do in spectral graph theory. For example, approximation of personalized PageRank. So I think that was their motivations, that they come to the similar formulations like this. Oh, they also say explicitly that then one may also use generalized PageRank score. So they know that this is related to PageRank scores. So DGNN is called proper if F1 and F2 is in the WGNN and AGG are injective mappings, as long as input features are all countable. So here, as I said, the first strategy is just put it as node features. We get these distance encodings, and then we just augment it, concatenate it, let's say, to have better node features rather than the standard. And then they talk about the expressive power of that. And then the limitation of this distance encoding GNN. But the second strategy that I said I'm interested is like this. We use controllers of message aggregation. So what do we mean by that? It only uses the distance encoding as initial node features. So we further consider leveraging DE1 between any two nodes to control the aggregation procedure. So the representation of power of this formulation is at least no worse than the previous, because the later one is specialized by aggregating the nodes with this one. Shortest path distance is 1 between any two nodes. So this is a subtree rooted at a node. So in the left, we see that the black nodes are the target nodes, so the structural representations are to be learned.